do. Okay, so let's get started on tonight's talk, and welcome everybody. Welcome in particular to our speaker, and welcome to the very large audience that your very intriguing talk has attracted, Neil. I'll just introduce Neil to begin with. So Dr. Neil Phillips has posts at Stellenbosch University in South Africa and University of Melbourne in Australia. He did his PhD working on high-grade metamorphic rocks around Broken Hill in Australia, famous mining place. And after that, he worked on underground workings and drillings in the Kalgoorlie area, synthesizing data ahead of development of the super pit there. He and his colleague, David Groves, developed many of the ideas used in Western Australian gold exploration since the 1980s. So Neil is really got a towering reputation in the sector. And just a plug, which I'm sure he will appreciate, is that he has just published a book called Formation of Gold Deposits, which you can all rush to purchase from Springer. Presumably it's available on Amazon after the talk. So at this point, I'm going to hand over to Neil to tell us about granites. Thank you.
Thank you very much for that welcome. Let me see if I can share my screen. There we go. So while that's warming up, yeah, thank you for the welcome. As I say, it's morning here, and nice time of day, and I'm looking forward to speaking again, having done something similar to this on gold about 12 months ago.
Yeah.
Now, just checking, Gillian, is that okay? Is the seeing the screen and the full?
It looks perfect to me, Neil.
Okay.
Yes.
If there's any problem, anybody, just drop me a message in the chat box.
Okay, I'll talk. I'm talking about granites, and granites are something, I won't say universal, but you can find them on every continent. They're not too hard to recognize as a rock type. They're a lot of fun, and I'll talk a little bit about their shape, what goes on in 3 dimensions, and that's this pipe versus pizza type story that we've gone on about for a little while. I am going to draw some of my examples from the Strathbogie granite in the middle of Victoria, about 2 hours drive north of Melbourne, which is where I'm based. And I'll show you some slides from there, but from other places around the world to show it's different, but it's not the only granite in the world with some of these features. I put this in here, so John, when you put this up for people later on, they can go firstly to the earlier talk, which Christine's given me the links there, and secondly, down the bottom, that sort of question that often comes up after this of, well, that's all interesting, but there's a few things on granites. I just need a textbook that's easy, but not sort of super hard, needing a PhD to read. And this paper here of about 30 pages was really written just for that purpose. I mean, John Clemens is well known in the granite field, and he put out some really good notes at Stellenbosch for his second and third year students. And I said, John, this is crazy. You need to get that published so people can use it, and so people like myself can refer to it when we speak. So I've got colleagues in Stellenbosch, all around Victoria. We've worked on these things for quite a long while. For me, it's a hobby. Gold has been my business. And this type of countryside, a lot of people think it's very nice. Certainly the people who live up in these type of areas derive a lot of pleasure from the boulders there, the rock climbers do, and so forth. That happens to be in Victoria. I think you'll recognise the same type of features there, and that's northern Portugal, famous for a lot of its granites. And I'm going to talk a little bit about why we get these rounded type characteristic shapes in granites. I'll come to that. Quickly, some of the things, the main features, what makes a granite? Well, it's an igneous rock crystallized from a molten rock. It's really got three main minerals. The big white things that stick out are feldspars. The glassy bits, and there's 20 or 30%, 20% perhaps here, is quartz. There's a lot of the finer material is feldspar, and some of this black material is mica. And we've got white mica and black mica, and this happens to be black or biotite. But really, the key things are feldspars and quartz, and for granite. That was from Australia. This one's from Cornwall. And again, the feldspars there, a little bit more quartz, and a little pocket of tourmaline with quartz there. But for me, the other side of the world. So quartz, feldspar and micas make up these things. And it doesn't matter whether you're in Western USA or Argentina or whatever. A lot of these things are relatively similar. Now, as I was talking, I was admiring the map behind Gillian's right shoulder of the Pacific, and I'm going to focus on the Atlantic just for a moment. What I'm going to draw attention to is where granites aren't, because it's quite revealing, and it's been known for decades that the oceanic environments, be it the middle of the Pacific or be it the middle of the Atlantic, are characterized by basaltic rocks, basalts, those type of things, and not granites. And if you want to go and find granites, lots and lots of places to go. I mean, you can go to Cornwall, I mentioned, Ireland. These are absolutely world classic field areas. Spain, northern Portugal, France. It goes on and on and on. Some really good ones around South Africa. They are a very important part of continental environments. But when you start going to these islands, and I have not been to many of them except the Azores, when you go to these islands, they're not made of granite. I'll take this a little bit further. I'm going to go to the Azores here, where I've spent a little bit of time. Basically, it's a 3-hour flight west of Lisbon. So you're 1/3 of the way across to New York. We're in the middle Atlantic ridge on this same trend from Iceland, much better known from a tourist point of view. And a line basically coming down there that the split the Atlantic Ocean as the different sides moved apart. So let's go to the Azores. We've got volcanoes, they're pretty young. This one here is 2,000 meters high, and you can sit right on the top. And as you sit on the top, your backside will be getting warm from the continued activity. And I don't mean hot lava here, just warm, so pleasantly warm, but it's still going. And the thing I want to point out here is everything along the sides here is made of basalt, because this is basalt that's come out from these. Other end of that same island, we've got active volcanism here in, at least in my lifetime, and that's the last for the Azores, but it'll happen again. And this technically is this here, what you're seeing is the exact western edge of the European plate. And one of the other islands here, you can see the basalt all the way around here, and they're using it extensively. But what is this white stuff? What is this and this and this? And it doesn't take long to have a quick look and say, well, that's granite. And so it's always fascinated me. It happens to be an Australian pizza shop here. Why on earth that's named, I don't know. But that's on St. George Island in the Azores. There's the basalt they're using, and this is granite. Now, that granite hasn't come from the Azores. That granite has come from northern Portugal. So they've put a lot of effort into decorating their islands with granite. So they obviously value granite just like I do. So that's the Azores, and that's basically the mid-ocean setting where granites are absent or virtually absent. And we'll go now onto the continents. And it's the process, the plate tectonic type processes of rocks going up, going down, being deformed, being heated and so forth, that are part of the story of why we get granites there. did this little cross section to just in 2 bits to talk about the difference between our volcanic rocks and our granitic rocks. Our volcanic rock melts at depth, and I've said 10 to 15 kilometres here for this particular area, but this could be 100 kilometres, tens of kilometres. And it comes out as a volcano. It might have a crater, and that's pretty visible. Or the rocks might melt, and for different reasons, they may not come to the surface, and they crystallise underground, and we're going to have a granite here. And that granite will cool more slowly, and as it cools more slowly, the grains grow larger, and it will probably, normally, be much easier to look at this without fancy laboratories and whatever, but just with eyes and perhaps even a hand lens and say, yeah, I can see the minerals. I know what this is. This is a granite. It's very like we might have at home. You go and look at these volcanic rocks that come out. It's often much harder. They're fine grained, they cool quickly, and it's basically a different field for a different group of people often. Now, there's what it was, and I'm going to cut the top off through erosion over millions of years, and in doing so, you've still got your volcanic rocks there in brown on the left, but we've trimmed off the top, the sedimentary rocks that were overlying the granite, and back here, the ones that were basically stopping it get to the surface or sitting on it and baked by it. So now we walk across the land surface. We've got a bit of a plateau there. We've got little bits of the sedimentary rock, but we've also got a lot of granite sticking out at the surface. And as erosion goes on and on, we'll see more and more of that granite, and we'll cut deeper into it. Now that process will be happening on every continent every day of the week. Sideways a little bit to this characteristic, this iconic feature, not universal around the world, but very, very common in a lot of the countries where we live, of the round boulders. And I say that because in a glaciated area, perhaps in Antarctica, things would be very different. There's a process here that is common, be it in North Portugal or be it in England or be it in Australia, that develops these round, call them boulders, call them tors. It depends if you're technical geologist, a rock climber or whatever. And it's these type of features. And when we look at that, and there's one of these tors or boulders over there, there's lots and lots all through here. And this classic one here that actually sits on the front cover of Applied Earth Sciences, the journal I referred you to in the second slide. And you sit and say, well, how did they get these things up on top there? How on earth did this happen? And there is quite a reasonable explanation for that we've had in the field for some period of time. And you get these great big ones here. There's my field vehicle. So this is a pretty large blob of granite. This is from Portugal, and clearly they're using granites here to stop the house blowing away, or they've built around it. And they've actually built their whole village around these rather than try and move them with a bit of creativity. So here's my starting point. This is, we'll call it 2 hours north of Melbourne. It's just a little outcrop in a very small creek with a very small waterfall. The important part here is these cracks, and we call those joints, but we'll call them cracks also. Cracks through here, a series of parallel ones, right? And so there's 1, 2, 3, 4, 5, 6 or 7 running sort of northeast on here. And there's also ones running across here. They are close to right angles and there's a flat surface. So there's a number of cracks there. And we go across to a slightly larger creek that's not particularly material, except the outcrops are very good here to show what I want to show. Standing where we are, looking across the other side, there's lots and lots of these vertical cracks. They're over here on the right, they're actually on the left. If you look carefully, we've got horizontal ones right across here, but up in the top right, there's horizontal ones. And if we could swing around to the right and look up and down the creek, in other words, what is the creek following? The creek is following a third set, which are parallel this way. So here we've got vertical set north-south, vertical set east-west, and a horizontal set of cracks. And these cracks have developed because our molten rock cooled slowly underground, and as it cooled from 800 degrees to crystallized to become a solid and then to room temperature, the volume changed. And as the volume changed, just a little bit of give and take, and these cracks develop in response to where's the land surface and also stress fields at the time. But the important part is we've got cracks, and in this case, it's 3 orthogonal joint sets. So there's our block of granite. It's got these orthogonal joint sets, and we're now going to undergo some chemical, a little bit of physical, but particularly chemical weathering, where water gets down those cracks. That's just rainwater from yesterday, gets down those cracks. It might go down those cracks and then come out further down hills as soaks, which are very common in granite country. And let's go to the next stage. What we've got here is there's your granite around the bottom. Nothing much changed. It's still got the cracks, but the upper part has been altered to soil. In other words, the granite's all weathered. The quartz is still those glassy quartz grains that one might slip on surface, but the feldspar's all gone to clays. And those clays are still there at the moment, but let's have some rain. Let's wash the clays away and some of the sand, and we now erode the surface down. And as we do, these unweathered blocks start emerging from the surface. Well, they don't actually emerge from the surface. They stay where they are or even go down, but the surface goes lower, leaving them sticking out. And that's the sort of countryside scenery I was describing in the first slide from Australia, the slide from northern Portugal, and lots of other ones. And over here, we've got one that now is balanced. It's just as it's progressed and had the soil removed from under it, it's ended up on top of the one below. And you can get 2 or 3 of these sort of piled up in places. So lots of unusual shapes end up, and this is part of our granite landscape. So that's perhaps how we get these rounded tors, boulders. I'm going to turn to another side of the granite and ask this question. Certainly when I was in undergraduate, and a lot of other people my generation, if we listened to anything, we would have heard that granites and these things go as pipes down, 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 and don't you worry, they just keep going to great depth. Now, some things might, and kimberlites with diamonds might, and so forth, but there's a lot of questions today and saying, hey, this may not be the total story, and instead, these might be much thinner than you think, and of a different aspect ratio, a different thickness to width ratio. And some of our evidence is drawn from, in my case, gold mines, particularly in Western Australia, where you might have one of these, and as you mine through it, you mine out the bottom and you say, hey, this only went for 50, 100 metres, and now I'm in non-granite at depth. So I can think of several examples of that. But what we're going to do is we're going to go around the edges of that granite, the tips on the left and right, and see if we can see where the boundary between granite and not granite is horizontal, and are we looking at top of granite or bottom of granite or a bit of both? Quickly zooming in, Australia here. On the right-hand side, Australia can be divided very simply into the older part on the west, Archean rocks equivalent to what you've got in northern Scotland. The middle part, the Precambrian rocks, not quite as old, but still old. And on the right-hand side, on the east coast, running right down there, is the Paleozoic rocks, much younger, folded up into our sort of slightly higher hills, and sedimentary basins, all these vast areas in between. So I'm going to stick down in that bottom right corner. I can't actually see it unless I move that around. And I'm going to look at that area there, and I'll zoom in on that in a moment. But just to give you an idea, it's about 10 hours drive across there. So it's vaguely in the dimensions of an England or a Portugal. That's that same area. Lots of different granite types here, because this has been a classic area where Australian researchers have looked at the granites because they make up so much of the terrain there, and these extend further north. And yeah, some pioneering granite studies there over the last 50 years. The different types are shown there. I'm going to actually focus in on this pink one that sits right in the middle with that very characteristic right angle bend. I've lost my pointer. I'm talking about this one here. So there it is. This is our Strathbogie granite. I'm going to show a few photos from that. And I'm going to look around this edge. And we're going to map some of this edge, and we're going to ask that question, what are we looking at? Is this a boundary between granite and not granite that's horizontal or vertical? Is it top of granite or is it bottom of granite? And the answer is going to be all of those. It's Devonian in age. It intrudes Siluro-Devonian sedimentary rocks. And we'll look at this boundary, why I say things like it's discordant and it's sharp and so forth. And it happens to have the Victorian Gold Province around it, but that's a different story altogether. And the irony from that introduction is I work on this granite because in the fieldwork, it relies considerable permission and working with the communities. And I probably got about 800 landowners, and I need permission to go on each of their ground as I do the work. And in so doing, I can't be saying, hey, I'm doing some research on granite and also I'm pegging ground for gold or something else there. There's a clear conflict of interest. So it happens to be this granite has no gold in it, and it's a really clear-cut case of no, this is just research work. So it's very convenient that way. There's your granite, filling this field of view. One of our larger rivers, just cutting right through it. And I'm going to look at this a bit more. That's the slide we showed earlier, and I removed a little bit for simplicity at the time, and you'll see the word cordiorites added on. So we've got our quartz, the glassy parts, we've got our white feldspars. We do have a little bit of mica. It's hard to see actually, and quite a bit of this, that's mica there, but quite a lot of that material is cordiorite. So we've got a new mineral here, and I use it sort of lightly, new mineral, and I'll talk a fraction about cordiorite because it's actually quite unusual in granites worldwide. And someone from Central USA might say, well, hey, I have to go 1,000 kilometres to find a cordiorite bearing granite, and we've got it everywhere. So there's something different about different patches around the world, and we ask that question, what is it telling us that this one's so rich in cordiorite? What you're looking at here is a lot of this is cordiorite. It's the mineral cordiorite. It's not, it's tabular in shape, table-shaped, and it's all these bits here and the bits here, and it's not perfectly shiny black like mica, but it's slightly dark green coloured, a little bit of chloride alteration. There's a crisp, clean one. This is cordiorite. This is cordiorite over here. There's two more bits down there. So there's quite a bit of it. But it needs one to be alert to look for it. And it's, for those interested, it's a iron, magnesium, aluminium silicate. It's got no OH on the end. And so it's a high temperature mineral. And this is telling us it's a high temperature granite melt. There's our Strathbogie granite. It's 100 kilometres on the dimension there. And all this is doing is addressing that question, well, where in the granite do you find cordiorite? These are some of our field date waypoints, and it's simply a map of the cordiorite grain size, 1 to 5, 15 to 25 millimetres. The message from this is it's everywhere. It's not just in the top left corner or the bottom right corner or anything like that. So this is a granite that's got quite abundant, few percent cordiorite over 2,000 square kilometres. Changing topic just slightly, and that is back to the geometry. We're going to home back on the geometry a bit more now. And if you look around the field, this is a plateau area. It's open farm country. We've got a little kopje or a little hill here with very rocky aplite, fine-grained granite. Rocky, not much chop for agriculture, and so it's left behind, left with a few trees on it. And we've got a boundary here. And it looks like a boundary between very good outcrop and very poor outcrop. But if we scratch around here, only a centimetre or so, we find this is a coarse-grained granite. So we've got a coarse-grained granite down here. We've got an aplite or fine-grained granite here. And again, just the hints of a subhorizontal boundary between these. And that type of photo with a little aplite top and this coarser-grained, less outcropping material underneath the subhorizontal boundary, dozens and dozens of photos around the plateau, spread over tens of kilometres. So it's quite a common sort of photo, that. And on the bigger scale here, what we're looking at is 10 kilometres across this plateau. We're looking at a bit of hornfels or the sedimentary rock on top. We're looking for sedimentary rock just in bits and pieces around the bottom. And most of this is our granite. So let's talk more about the shape of this granite, and can we say anything from our fieldwork? And this isn't the only way to tackle the question of, are we dealing with pipes or pizzas? It's a way, and it has to be blended with information we get from geophysicists who say, well, I've been modelling this and it could be this or could be that or whatever. So we've got to blend it with other forms of information. But this is an important contribution to that question on shape. There's what we were talking about, our pizza with steep sides our pipe with steep sides going down, 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 or our pizza, the granite sheet. And we're going to look around these little corners here and say, I've got a horizontal boundary and it's the top of the granite. I've got a vertical boundary and it's the side of it, or I've got a horizontal boundary, near horizontal boundary, and it's the bottom of the granite. We're going to find all of those. Hornfels, I'll just explain, that's the hard rock produced by contact metamorphism, the heating of the granite. And it's analogous to getting some clay, putting it in a kiln, and the soft and slushy clay will go to something hard, be it china, chinaware, or whatever. But it's that process of changing from clay to other minerals and completely changing its property from soft and sloppy to hard. And that hard part, or the hornfels hard rock, is what makes the edge stand up a little bit because it's acting as a hard rock and resisting erosion. So here's our choices. We've got the hornfels, the sedimentary rock that's been baked, sitting on top of the granite. We've got it across to the side, and over here we've got it underneath, and we're looking at the bottom of the granite here. To find the bottom of the granite in the sort of terrains we deal with in Australia is very, very uncommon. Here's an example. It's only of local importance, but there's a piece of granite. This is hornfels sedimentary rock heated up, and it's obviously a near horizontal boundary. I use the word discordant, and this is what I mean. All these rocks right through the upper part here are granite, and one could take one step forward, have a look, and convince oneself that's what it is. And down here, all of this is hornfels. This is bedding, in other words, how the layers were laid down. And what the granite's done is it's come in and cut right across. It's completely truncated that boundary. That's sort of probably following bedding a bit, whereas this one here is just cutting right across. It ignores all this bedding and just says, right, I'm coming in, I'm pushing, I'm just cutting and making way for myself. So nice boundary there. And it's pretty easy to put left foot here, right foot there, and say, I am straddling the boundary, and then to just record on your map or with your GPS waypoint and say, right, I've just recorded a boundary of the granite and hornfels there, and I could take another reading here, another reading here, and clearly you don't want to take too many when you've got 2,000 square kilometres to deal with. But this is a lovely situation where there's a lot of places like that. One looks at that and says, oh, it's a bit of a jumble, but that material over there is all granite, and it's actually quite different from all this material here, which are these angular bits of hornfels. We can go up to each and check it, and I'd be putting a boundary through here, and I'd say, right, I'm pretty comfortable I can run a boundary here between hornfels close to me and granite over on the left. And that's really useful because, first of all, we can follow that, and we follow down this valley up here, right up over the hill, and we can follow that for 250 kilometres. So that gives us a good feel for what it's doing on the land surface. And there's a lot of confidence here because you might argue, well, you don't know exactly where it is here. Well, in 250 kilometres, that doesn't really matter. And with a GPS, the accuracy is probably somewhere around a small number of metres, maybe 2 or 3 or 6, it doesn't matter. But we're getting a dot here and saying that's the boundary with confidence, and here and here and down here and so forth. It's actually looking across the same river we looked at before, but I'm interested in the foreground where we're getting these boulders. But if you look down here, what we're seeing is bits of the sedimentary rock. And there's an element of trusting me on this. I mean, it's clear to see it's different, but one does have to get down and have a look and say, yes, I'm happy that's what it is. But it's not hard to do in the field. So somewhere between there and there, we've got a boundary. That boundary comes up to here. But this is all hornfels, so it goes down to here, and it goes down there. So we've got a right angle bend there, a right angle bend there, and although that looks like scruffy outcrop to some people, you're going to map that boundary and the right angle bends in with a huge degree of confidence at the relevant scale for the whole granite. And two things come in mind. I mean, we started this work in the 70s, again, as part-time sort of enjoyment, using maps and air photos. And when you look back now and say how much easier it is with global positioning system using satellites to say where we are, and geographic information system, particularly we use QGIS. It's free software, and instead of making map after map after map and putting on little crosses and that for cordierite or circles for quartz or whatever, we do this electronically, and you can just call up a diagram of show me all the cordierite above 5 millimeters, and I can get a map of that quickly. The global positioning is great because instead of going in thick bush and trying to work out which tree is the one you're under and where you are, or pace and compass, you can just walk to your place and say, I am on the boundary here, left foot, right foot, crossing it, press the button, and you've recorded a waypoint as accurate as GPS is going to get you, which is plenty good enough. We'll see some of the results of that. The outcome of a lot of that mapping is what we call a step and stairs pattern. And I think that terminology possibly came from the Wimsill and coal mines in northeast England. So other people can check that up, but Francis and others used that at least 50 years ago for what they saw as across, up, across, up, across, up as the dikes cut through the coal measures. Here's a little bit of mapping. There's the right angle bend we looked at earlier just for reference. This arrow shows where this map is, and there's a whole lot of maps all the way along this boundary, all the way along to here and up a bit. So there's your 250 kilometres around to about here, and the rest is not relevant because it's a different rock types on the side. It's just sands and other things. If we go up to here, this is obviously, I hope people are comfortable with contours and those type of things. this is obviously high country here. It's a bit of a ridge. And what the boundary is, and these are waypoints of the boundary where we can sort of put left foot on one side, right foot on the other. In this case, it's granite over here on that side, and it's hornfels there. And we can straddle the boundary, and we can see it comes down here, down here, down there to here. And across there, it's very close to horizontal. So it's roughly following a contour. And in that case, I'm going to jump ahead, that's probably a horizontal contact between hornfels and granite. And in this situation here, the granite is downhill, that's where the rivers are flowing, and the hornfels is uphill. So this contact here is a contact of the top of the granite with the hornfels over the top of it. Top of granite. So let's come through this little saddle, and here we suddenly trace that down 300 metres. So 300 metres vertically straight down here. It's clearly not horizontal, it's cutting right across the countryside, and that's probably a vertical or close to vertical boundary. But what's happening here? From this point onwards, it's following contours again. And as it follows the contours again all around here, we're going to make a generalisation saying, again, that looks like a horizontal boundary between granite and hornfels. And the big deal is, if that's the horizontal boundary, uphill, very steeply uphill, you've got granite. Downhill where the creek is, you've got hornfels. So we've now gone, and this is all bottom of granite. We said this was top of granite, and this is bottom of granite. So in this particular map, and many others, in this particular map, we've got a fix on the top of the granite. It's close-ish to horizontal up on the top right, and we've got a fix on the bottom of the granite, which is close to horizontal, and probably 250, 350 metres vertically different between top and bottom here, with a very steep joining part. And that's the sort of step and stairs, if you like. Across a lot, steeply up, across a lot. I'm going to show that again. This is a little bit further west. We've got a significant highway and big river along here. And we've got a hillside with, we know there's hornfels all the way over here. And we know there's granite all the way down there. But it will be interesting to know what's the boundary between those two. And so we're going to map in this fairly difficult area. That's 300 metres vertically there. I've turned the map upside down, and there's a reason for that. Bergen Peak is that peak, and this ridge coming all the way down there of hornfels is the ridge coming all the way down there. Oops, sorry. Halfway down this slope, well, if we start here, we're on the boundary, granite on the right, hornfels on the left, and it goes steeply up. And that's represented by A to B up here. Then it goes horizontally across to C, following on the left. Then it goes vertically up to D. And at that point, we've got this amazing situation where the boundary sits on the 300 metre contour all the way around to there. For 600 metres, it's wrapping in and out the valleys, and it's very convincingly horizontal. It's following a contour. It's following a 300 metre contour. And in a lot of places here, you can put your foot down, and the front part of your shoe will be on hornfels, and the back part will be on granite. So it's really well defined, and it is in fact what we're looking at. We're looking at the top of the granite with those little cliffy areas, bits of pegmatite, bits of vugs, different material, and that's making that light colour. And I'm going to move so I can see it again. Comes across, and then it actually goes vertically straight up here over the top, which is this part here, and then down the other side, and on and on and on, continuing doing this. But this is just a really nice example because you can get across the other side of the river and look at it like this and see it so visually. So that's another step and stairs. Up, across, up, across, up, across, up, across, down if you like, or up. So it just goes on and on like that. What we can do is we can then look, we were just here, you can just look at the boundary and you can say, okay, flat areas, and we've seen some of those, and we've seen steep areas. And you can mark those out and say, just colour in the steep ones in blue, and I'm going to ignore those from now on, and colour in the flat ones with red, because I'm going to pay attention to those. The flat ones can be either top of granite or bottom, and we'll separate those out like this. The red ones are top of granite because Hornfels is above, and this is all top of granite around here for many kilometres. This is probably mostly bottom of granite, bit of top of granite, bit of bottom of granite. And these are metres. So we can see the top climbs from sort of 180 up to sort of 500, and then down here it goes down a bit. This is a separate body, and this body is all bottom of granite, around 200 or 300 metres above sea level, and top of granite 500 or 600 metres above sea level. And so again, hinting at 200 or 300 metres thickness, but not 5 or 10 kilometres of thickness that a pipe might be. So again, we're looking at a sheet here, and it's very difficult to demonstrate kilometres of thickness of these bodies. In fact, we're struggling to show anywhere where it's much over 500 metres thick, despite being 2,000 square kilometres. And for those who follow granites a bit, the type of indications of top, like pegmatites, vugs, tourmaline, are very, very common around that area, which is this top part, and pretty much absent around here, which gives us quite a bit of confidence that what we're mapping in the geometry is matching what we're picking up here in looking at the rocks and trying to map out where you find pegmatites and tourmaline in particular, and top part over here. This is what I mean by pegmatites. Slightly lighter coloured granite, it's actually finer grained, but this coarse grained material through here is pegmatite, and these patches here are tourmaline. And you look at a shot like that, and that could easily be Cornwall, could be Southeast Australia, but it's these tourmaline, very common near the top of granitic bodies, not just near the top. So we're getting hints there. We've seen quite a bit of the floor part where we're mapping out bottom of granite. We had that in green on one map. So we're mapping it out as bottom of granite. We're doing it over kilometres. It's not just 1 outcrop of 10 metres length. And we're also mapping out top of granite for many kilometres. And I swing back to this. What we're looking at there is we're looking at the bit of Hornfels over the top. So that's top of granite, comes down here, and all of this would be bottom of granite with bits of Hornfels in the foreground, or just below the granite, with all of that being a granite sheet. And again, it can't be more than sort of 200 or 300, maybe 400 metres thick, but anything but a pipe. And so that's why we talk about these things as pizzas. And the aspect ratio of this overall might be 300 or 400 metres thick and 100 kilometres in length. So it's an extremely thin pizza. I'm just going to finish with some other colleagues. I've done a bit of work with the people at University of Porto. They're in northern Portugal, and they're very much in Portugal's granite country. This is a plant where they cut the rocks up and make granite bench tops and all that stuff that gets exported around the world, including for pavement on the Azores. Prof. Ferdinand Noronha from the department there has been mapping in that area on the granites for years and years, and they've shown me around a bit, and this is some of the mapping, and I'd be absolutely certain this type of mapping exists in England because it's one of the best mapped parts of the world. But it's a map 30 or 40 years ago, and it's exquisite. It's got good contours and those things, but using air photos, he must have walked around this and carefully got in the boundary between granite, which is this part, and hornfelses and other things which are this part. And I've been able to just take this sitting in my office in Melbourne and find every place I think this is horizontal, and sort of say, well, that's a horizontal part, and that's that and that and so forth. So a lot of this looks a horizontal type boundary, not a pipe-like body. And you can also look out, I mean, it just so happens there's a major creek or river down the bottom here, and the granite is low, and so a lot of this is going to be topper granite. I'm not saying everything around the world are going to be pizzas of these granites, and clearly some aren't, but I think a lot more of these will be found when people either go back to look at much older, very good mapping, or get out there and have a look and say, well, maybe we can, rather than looking at the mess and saying, oh, it's all too complex. And I think it's something that can be done very easily and a lot of fun. I'll leave it there. Thank you very much, and more than happy to take questions.
That was wonderful. Thank you very much, Neil. It's certainly opened my eyes about granites. So my colleagues and I have been thinking about all the granite in Iceland just recently, and we're thinking of doing a bit of work on that because nobody seems to be able to explain where they come from. But would the audience like to pose questions? People can either put their hands up, or they can type their question into the chat box.
This is John Waring here. Can you hear me?
Yes, I can, John.
Yes, I couldn't help making a comparison or contrast between the granite exposures and the granite exposure in the Cheviot Hills, that's in northern England. In the Cheviot Hills, the part of the Cheviot Hills is covered in Devonian andesites, and actually beneath the Devonian andesites there is this huge granite intrusion, which is to my mind, is in direct contrast between the granites that you have explained and the adjacent hornfels. Basically, I don't have any question. All I want to do is to point out the difference between the granite exposed in the Cheviot Hills, which is covered by andesites, and the granites that you have been looking at, which is more or less surrounded by hornfels. It's just a remark, it's not a question. Basically, sorry.
Oh, I was going to say, my story is anything but complete. I was going to go back to one of our maps, but I'm not sure I can easily. Yes, I can. Of course I can. Because what you're talking about does exist. I've talked all about the southern margin where the granite is against hornfels. And you're making the point that that's a contrast to what you've got, and that's completely right. What I haven't mentioned at all is this area up here is all rhyodacite. Now, I'm going to annoy the igneous petrologists, but rhyodacite and andesite are not vastly different. They're igneous rocks that come out at the surface. They're roughly the same age as the granite. And we didn't work on this boundary here because it's, well, it wasn't going to show what we're trying to show. So our answers on the geometry, really, we have to be a bit careful and say, well, we've only worked on that part there. We've got soft and sloppy sands from yesterday up here, and we've got a great big acid volcanic complex here, probably only 300 or 400 meters thick, but analogous to your andesite, I think. Now, what's in the granite, your Cheviot granites probably are quite different from this, but you might have areas where it's up against hornfels. I'm not sure.
Yes, the only remark that I wanted to make was the fact that in the Cheviot Hills, part of the Cheviot Hills, a large part of the Cheviot Hills is composed of andesite, and then lower down, so to speak, you have this granite intrusion, which has sort of, and there are places in the Cheviot Hills where you can actually see the contact between the Cheviot granite and the Cheviot andesites. And yes, this particular map that I'm looking at does show some similarity in some respects. Thank you very much. Just a remark,
okay,
not a question.
Yeah, this area here would be the analogy to where you've got a contact between andesite or acid intermediate volcanic and granite. And I'm suggesting that maybe your granite somewhere else has this type of boundary as well. That's a complete guess. I really don't know.
I was just suggesting that the Cheviot granite underlies the Cheviot andesites.
Yes, that's fine.
Oh, that's fine. Thank you.
Mm.
Thank you. I'll shut up now.
No need at all.
We have a question in the chat box from Leslie Collins. Why the predominance of cordierite, which we don't see here?
It's really, that's a global question, actually. I mean, I don't understand it, but there's cordierite granites in Europe a little bit, but there's cordierite everywhere in the southern hemisphere, or at least to South Africa and a lot of Australia. And I mean, as a person brought up in Southeast Australia, I had cordierite all through my high-grade metamorphic rocks at Broken Hill, cordierite in the contact aureole here in the Hornfels, and cordierite all through the granite. So you come from a very different perspective than, now I've forgotten his name, but a very famous granite mapping person living in northern England. Published a book on this, and he said it was only late in his career that he ever saw cordierite in a granite. And yeah, so it's something different about what's going on here. And if we look at the mineral itself, several things come up. First of all, the high AL tells you that these are aluminous rocks. It's probably to do with melting of clays or clay-bearing material. The fact it's got no OH, it's an anhydrous material, tells you that it's going to be high temperature as opposed to the micas that are a little bit less so. So high temperature, probably melting of sedimentary containing material. And the other thing is that composition is very, very similar to garnet. The only difference is the numbers. So you're juggling around the ratios of FeMg, Al, and Si. So you then go and look at garnet-bearing granites, and there are some, and cordierite-bearing granites, and saying, what's the difference? Well, garnet is a very dense mineral. The closely spaced lattices and so forth. Cordierite is exactly the opposite. Cordierite is a very undense or open space mineral. And again, we'd be looking at the higher density. The garnet responds to higher pressure, the cordierite responds to lower pressure. And so we've got a qualitative relationship there between the higher pressure rocks will be garnet, the lower pressure rocks will be cordierite. Now, I know that's a little simplistic, but it works particularly well. So we're saying a granite that's emplaced to high level, so just below the surface, a granite that's very hot, and a granite that formed from melting of sedimentary material, as opposed to just basalts or anything like that. So we can say quite a lot from that cordierite. There have been different ways on how cordierite might form. It might be the hornfels falling into the granite and other things like that. Those things do not fit the distribution I showed. This is something that's crystallized from the melt. So it's been an important laboratory for understanding cordierite in magmatic rocks. Sorry, long answer, but it's a fascinating story, this cordierite in this granite, and it's been just sort of one path of our research for decades.
Maybe I could ask, where do the so-called batholiths of Western USA fit into this, in Yosemite and all that?
To the best of my knowledge, no. If we're talking about cordierite, sorry,
I was talking about the granites in general.
Oh, well, there's the compositions of all of those down the Pacific eastern margin are not these highly perluminous ones that we get with cordierite and other things. The shape of them, there are certainly indications that of pizza-like shape, and for those lucky enough to have been to Torres del Paine in southern Argentina, or is it Chile? I haven't been there, but there's photos on all tourist brochures, and if you look carefully at those, there's a hornfels that goes across horizontally. It's tens of meters thick, and it's got this step and stair geometry, and so they advertise it on these cruise pamphlets and everything. So that's a really good example of it in the flesh, where you can see the whole lot. And right under Mount Everest, there's it's a muscovite-bearing granite, and Mike Searle from Oxford written a lot about the Himalayas and the geology, and again, interesting there because you can look and sort of say, right, there's something that's horizontal, and that's the muscovite-bearing granite. So a lot of these are not pipes. I'm not saying that there's no pipes. I'm just saying when one starts looking, there's a lot of good examples of pizza-like geometry.
I see. Kind of different from what one remembers from one's Geology 101.
Absolutely, yeah. I mean, I had to undo and learn again. The Yosemite one's interesting because you've got huge faces there of 100% outcrop, and Al Gleisner had a PhD student, very keen rock climber, and he just spent his whole time working on that kilometre high face, just hanging from a rope, I think, measuring and mapping in the very fine details of the granite, and came up with quite an interesting story on how he thinks these things are emplaced. And he could do that because he had perfect outcrop.
I see. Okay, we've got one question, which maybe we should make the last one, from Chris Burridge. I've been to Torres del Paine, and now that you've said that about the hornfels, it all makes sense. A pancake, thank you.
Yeah, it's funny when I mean, those photos will be in thousands of collections around the world, and it's only when you sort of go and say, what about that? You realise that it's there. It's staring at us in the space for 20 years. You read all the papers on it, and it's not really mentioned clearly as a step and stairs. I've also seen quite a lot. Oh, I was going to say, I've seen quite a lot of that on open pit faces in gold mines. So you got a 200-metre face and you see these pegmatite dikes stepping up, stepping across, stepping up, stepping across. So it's, again, sheet-like as opposed to pipe-like.
Comment from Leslie Collins. I believe that the Cornish batholith is now thought to be a series of pizzas rather than one huge intrusion. Thanks for a great talk.
I'm sure they haven't been swayed in the last 5 minutes by my talk. No, that's great. Yeah.
Leslie Johnson
but that's
posts.
yeah. Sorry, you go on.
Leslie Johnson posts. Thanks very much for this session. Learnt stuff, but I can apply it in the field. Thank you.
Some of this field work is it, I was just going to say some of this field work is things that anyone interested in nature can do, and I'm more than happy to sort of suggest what someone can do if you wanted to find this around the Cheviot Hills or anywhere else. It's just a really interesting project if people want to get out and map something and then take it to other people and sort of say, what do you make of this? Anyway, happy to help.
Chris Burridge posts, we await further instalments of this research. Do come back, Neil. So they're working you like a slave, Neil.
Talk about pressure.
Maybe Neil was asking me earlier about Neg's field trip. So can someone speak to a Neg's field trip, which has looked at granites recently?
Well, the only one I can remember is it last year, I think it was Ian Kill took us up the Cheviots. I'm ashamed to say I can't remember the detail of it, but I do remember him actually identifying a boundary. We took quite a long walk up. So I don't know anyone else can remember that, but I do remember that it was quite a long walk up the valley, and he took us to a boundary between the granites, and I'm afraid I can't remember what was the other side of the granites, but it was that was. I think I might have made some notes. I'll go back and look at those. But that's certainly pertinent. I mean, that would be interesting to do that walk again in the light of what we've, learned today, I think.
Ian Turnbull asks, do you have a paper about this?
We have a few papers on the Strathbogie granite with some of these photos. And so it depends a little bit on what you'd like. I'm happy to answer that afterwards, but if you wanted on the detailed petrology of the cordierite and the melting, that's something that's available. If you wanted something on the mapping of the boundary in the field, that's available too. So different ways to answer your question. So do send me an email afterwards and say what you'd like. Otherwise, I could send a batch to Gillian, but that's making a lot of work for her. So just come to me and say, I'm just interested in X.
Would you be happy if I posted your email address in the chat box?
Yep, more than happy.
Okay, there you are, everybody. And Andrew has asked a question. I have an unrelated gold question. I had a backpacking job working for a gold exploration company out of Perth in 1990. I visited Big Bell Mine near Kue several times, and it was struggling with ore grade. I wondered if it is still open.
Big Bell is a real favourite of mine, and it's loaded with cordierite. It's one of the very few gold mines in the West that has. But yeah, I've spent a lot of time there. They're companies, if you look on the internet, that say they've got a Big Bell North project, but that's marketing the name, and they're about 50 kilometres north and whatever. So I don't think much is happening at the moment. They've struggled a little bit with grade, as you say, but also it's a case of geology too. I mean, they've got different material, different ore material, and therefore they different ways to crush it and different requirements. And perhaps they didn't quite get that right in the late 80s and early 90s, around that time. I've got a publication or two on Big Bell if if you're interested.
Okay. Well, I'll put your
I would be
email in the chat box. I'm sorry, carry on.
Thank you. Thanks, Jill. Yeah, I was saying, thanks for that answer.
Okay.
Okay, so I don't know if there are any other questions. If so, post them or ask them quickly, or else maybe it's time to move on to thanking Neil tremendously for giving us this lecture. You've got a fantastic audience, Neil, and some really interesting questions, and I'm sure it's opened everybody's eyes that there's an awful lot more to granites than just, oh, that's granite over there, and we assume it's a big blob. So there's a lot more to it than that. So thank you very much indeed, Neil, and please join me, everybody, in giving Neil applause insofar as we can over a Zoom meeting. So
Thank you. It's
thank
been a
you,
pleasure.
everybody.
Right. Thanks very much.
Thank you. Thank you.
Thank you.
Thanks a lot. Bye.
Thank you very much.
Okay.
Yeah.
Thanks, Jill. I'll say goodbye.
Most welcome.